Hello, this is Dr. Hanaa Assil and this is Unit 5 of January 2021. This is in the Pearson Edexcel International A-Level Chemistry. Let us take a look at the questions. The first question was, when an alkene is added to a solution of potassium manganate, the purple solution turns colorless. In terms of electron transfer and oxidation number, how does the manganese change in this reaction? Remember, when we use potassium permanganate, reaction with alkenes or reaction with alcohols, it's an oxidizing agent. The purple color turns colorless. What is happening? This is the equation from the data booklet. The manganate ion, in which the manganese has an oxidation number of +7, changes to manganese 2+, and that is a reduction reaction. So what is happening? The manganate gains electrons and the oxidation number decreases. The standard hydrogen electrode uses an electrode of platinum coated in a finely divided form of the metal called platinum black. What is the purpose of this coating? So, we should know that the standard hydrogen electrode has hydrogen gas going in at a pressure of 180 m and temperature of 298 Kelvin or 25 degrees Celsius. We have a platinum wire attached to a platinum electrode, and this is dipped in dilute acid with concentration 1 mole per decimeter cubed. Now, why do we have this platinum coating, finely divided platinum on the platinum electrode? This is to increase the rate of the equilibrium between the hydrogen gas and the hydrogen ions in solution. Question 3 says, an electrochemical cell is set up to measure E cell for the reaction. So we have this cell or this reaction, and we want to write the cell diagram for this reaction. How do we write a cell diagram? We look at the two half equation. So we have iron solid going to iron 2+, that is our oxidation, and iron 2+ going tin 2+, changing to tin solid, that is reduction. Remember, when we write the cell diagram, we start on the left with the oxidation part. We have iron solid with iron 2+. Then we have a double line to indicate the salt bridge, and then we have tin 2+ going to tin. Since we have solids, iron and tin, then these are the electrodes. Remember, if we had only solutions in the half cell, then the electrode would have been platinum. The standard electrode potential for iron 2+ is -0.44. For the whole cell, it is +0.3. What is the standard electrode potential for the tin 2+? So we have this equation, and we are told the reduction potential for iron. Of course, what is actually happening is oxidation, so we need to invert this equation, and that means we need to invert the sign of the E cell. The other half equation is the tin 2+ going to tin, so we're going to invert the iron. This is now plus 0.44. We are told that the total for the E cell is +0.3. Then we can get what is the tin, and that is -0.14. Remember, what we write is the reduction potential. If we were trying to get the one for the oxidation, then we would have inverted the sign in order to write the standard electrode potential. Then question 4 says hydrogen-oxygen fuel cells can operate in acidic or alkaline conditions. What is the reaction at the anode in an alkaline hydrogen-oxygen fuel cell? Now we should know the equations that happen in alkaline electrolyte and in acidic electrolyte. In both cases, the overall reaction is the same. Hydrogen plus oxygen to give water, but the difference is the anode, which is the electrode that is negatively charged, negative electrode. This is where oxidation happens. So in an alkaline medium, the hydrogen gains OH minus, but in the acidic electrolyte, the hydrogen becomes 2H plus. The cathode is the positive electrode where reduction happens. So for the alkaline electrolyte, the oxygen changes into OH minus, but for the acidic, the oxygen changes into H2O. So the question is, what is the reaction at the anode? So the anode, that's the negative electrode, in alkaline, so this would be the correct choice. Which of these has the greatest number of unpaired electrons in each of its atoms? Well, let's see. In order to know this, we should know the electron distribution. So chromium, you should know that chromium has atomic number 24. So if we distribute it, we said argon, then we're supposed to fill the 4s before going into the 3d, but we said chromium is an exception because instead of 4s2 3d4, we said we're going to take one of the electrons in the 4s so that the 3d becomes half filled. But then that means that I have 5 unpaired electrons in the 3d plus 1 unpaired electron also in the 4s, so chromium has a total of 6 unpaired electrons. If we look at iron, we have only 4. If we look at manganese, we have 5. And if we look at vanadium, we have only 3 unpaired electrons. So the one that has the greatest number of unpaired electrons is chromium. Then this question says nickel is classified as a transition metal. This is because what? What was the definition of a transition metal? We said a transition metal or a transition element is one that is in the D block and one or more of its ions has incomplete D orbitals. So if we look at nickel, nickel is atomic number 28. That means 4s2 3d8. Now when it forms a stable ion like nickel 2 plus, we remove the 2 electrons from the 4s, so it still has incomplete 3d orbitals, and that's why it is a transition metal. So because it forms stable ions with partially filled d orbitals. Platinum forms a complex with this formula in which the platinum is complex to 2 ammonia and 2 chloride ions. And chromium forms a complex with the formula in which the chromium has 4 chloride ions. What are the shapes of these complexes? You should remember that the platinum with 2 ammonia and 2 chlorides, this is what we call platine. So we said we have cis platine and trans platine, and we said it is the cis that is used to as an anti-cancer drug. So it's used to treat cancer. Chromium with 4 chlorides, we said if the transition metal has 4 chloride ions, the chloride ions are large and they are spaced so that they are tetrahedral. So the platinum is square planar, and the chromium with the 4 chlorides is tetrahedral. What is the bonding between ligands and the central atom in these complexes? In any complexes, remember, the bond between the ligand and the platinum or the chromium, this is a dative covalent bond. Cobalt chloride is used as a test for the presence of water. This test depends on the fact that what? When we talk about test for water, we said we use anhydrous cobalt chloride. It turns from blue to pink. So the anhydrous is blue, the hydrated is pink. Iodide ions are oxidized by peroxodisulfate ions in aqueous solution. This reaction is catalyzed by adding iron to ions. Remember that we said this equation is an example of homogeneous catalysis in which the reactants and the catalysts are in the same state, so all are aqueous solutions. Now, the iodide plus the peroxodisulfate, we said this is a slow reaction because these are two negative ions that will repel each other. They're not likely to react. So we add iron 2 plus. Now, why does it act as a catalyst? Because the iron 2 plus reacts with the peroxodisulfate to give iron 3, and then this iron 3 reacts with the other reactant, the iodide ion, to form iron 2. So it is acting as a catalyst because the iron 2 is readily oxidized to iron 3, which is then reduced to iron 2. The delocalized electrons in benzene result from the overlap of what? Remember, we said the benzene is supposed to have 3 double bonds, but actually these double bonds are due to the p orbitals. There is delocalizing of the electrons, so all of these bonds are equal. Now, this delocalized electrons result from p orbitals, which are delocalized or spread around all the 6 carbons to form pi. The reaction of ethene with bromine occurs under normal laboratory conditions, but the reaction of benzene with bromine to form bromobenzene requires heat and the presence of a catalyst. The best explanation for this is what? Remember that when we react ethene with bromine, we said this happens at room temperature. This is addition reaction of alkenes. But when we do benzene, we said reaction of the benzene with bromine requires anhydrous iron 3 bromide as a catalyst and heat. Now, why is that? Remember, we said that the delocalized electrons in the benzene causes the reactant to be stable. So there is a kinetic barrier to the intermediate formation. That means the reactants don't react easily. So this would be the correct choice. What is the name of the compound shown? How do we name this? First of all, we choose the longest chain of carbons. So this is something with a but, not a prop. And it has the double bond ONH2. This is an amide group. So this is butanamide, and it has a methyl group at carbon number 2. So this is 2-methyl-butanamide. Separate 0.1 mole per decimeter cube the aqueous solutions of ammonia, butylamine, phenylamine were prepared. Which of the following sequences shows the solutions in order of increasing pH? So remember, first, increasing pH means we want to start from the less basic to the more basic. We know that all of these are amines, and we said the strength of the amine depends on the availability of the lone pair of electrons on the nitrogen in order to make a dative bond with H plus ions. So which of these has the lone pair of electrons on the nitrogen more available? If we have an alkyl group, alkyl groups are carbon chains. So R represents a carbon chain. Alkyl groups are what we call electron donating. So the lone pair of electrons on the nitrogen are very much available for reaction. That is more than ammonia. So that means the alkyl amine would be a stronger base than ammonia. When we have a benzene ring in the phenylamine, the lone pair of electrons are actually not available for dative bonding because they are delocalized onto the benzene ring. So this would be the least basic or the lower pH. So if we are trying to arrange them increasing pH, it is the phenylamine and then the ammonia and then the butylamine is the more basic with higher pH. The repeat unit of a polymer is shown. What is the structure of the monomer? Obviously, this is a polymer made by addition, polymerization. So we started with something that had a double bond in it. Now, where was the double bond? That's where the double bond was. So if we flip it around, it looks like A, not like any of the other choices. The repeat unit of a polymer is shown. This polymer could be, is this a polyamide or a polypeptide or both? Remember, a polypeptide is made of units made of amino acids. That means one side acid, one side amine. Is it a polyamide? Yes, it is a polyamide because it has an amide linkage, but is it a polypeptide? No, the units are obviously made of diacid and diamine, so it is not a polypeptide. The structure of a hydrocarbon is shown. How many peaks will there be in the carbon-13 NMR spectrum? How many different carbon environments? So if we look at these, first of all, it is sort of symmetrical. So the right side is the same as the left side. So we have a total of 5 different carbon environments, so 5 peaks. When a sample of a hydrocarbon is burnt completely in oxygen, 2.64 grams of carbon dioxide and 0.81 grams of water are formed. Which of these could be the molecular form? So first of all, we need to calculate what is the empirical formula. In order to do that, we need number of moles of each of them. So the number of moles of the carbon dioxide is, of course, mass over molecular mass. So it is this number of moles. And each mole of carbon dioxide will give 1 mole of carbon. So that is the same as the number of moles of carbon. Now, what about the oxygen? In water, we have this number of moles, so mass over molecular mass of water, but each mole of water has 2 moles of hydrogen, so that means the number of moles of hydrogen is twice of that. Now, if we have these number of moles, we need to simplify by dividing by the smallest, so this is 1 to 1.5. We multiply them to get whole numbers. So this is the empirical formula. C2H3 is the empirical formula, and you should remember that molecular formulas are multiples of these. So the one that could be a molecular formula is the multiple of this, or times 2, that would be C4H6. Benzene carboxylic acid may be produced from benzene in a 2-step synthesis. 8.24 grams of benzene carboxylic acid was formed. So the product, we got actual product 8.24 grams. That's the actual mass of the product. What was the mass of benzene? Now, we need to pay attention to the fact that each step did not have 100% yield. So let's start from the benzene carboxylic acid. We got 8.24 grams, so I can get the number of moles of that, the mass over molecular mass, but then this is only 60% yield. So if I were to get 100% yield, then the number of moles would be this. Instead of 60%, the 60% gives 0.0675. 100% will be how much? That is the number of moles if I were to get 100%. Now, that is the actual mass that we should get. Now, for methyl benzene, the number of moles is the same as the number of moles of benzene carboxylic acid. Now, going to benzene, the number of moles of methyl benzene that we have, which is the 0.11256.8 mole, this is the result of 45% yield. So if we were to get 100%, what would be the number of moles? So that would be the number of moles of benzene we started with. Get the mass, number of moles times mR. So the mass of benzene that we start with has to be 19.5 grams. So that in the first step, when it gives 45% yield, then we get the 0.112568, and then if we get the 60% yield of the other one, that would be the number of moles that we got in the synthesis. Then this question has some reactions of copper compounds, so we're having a flow chart with different reactions of copper compounds, and we are required to get what is the structure of P, Q, R, S, T, V, W, and so on. So let's take them one by one. So the first question here is what is P and what is Q? We are told that copper 1 iodide reacts with sulfuric acid to give P, which is a pink solid, and Q, which is a blue solution. So first of all, we're talking about copper compounds, and we did something to the copper 1 to get a pink solid. Obviously, P should be the copper metal. That is the one that is a pink solid or a reddish-brown solid. What is Q? Q would be, it's a blue solution, so it has to be copper 2+. So it is the complex of copper 2+ with 6 water. Now, let's ignore all of this part for now, and let's look at R and S. What is R and what is S? R is a pale blue solid. When we add copper sulfate to ammonia, remember when we add drops of ammonia to the copper sulfate, it gives a pale blue precipitate. Now that is R, so copper hydroxide with water as ligands. That is the possible formula for R, or you could just write copper hydroxide. And then when we heat this solid, it gives a black solid. We're talking about copper compounds. A black solid would be copper oxide. Then let's look at this part of the flow chart. The question said we had copper 1 iodide and we added ammonia, and it gave a colorless solution, which on vigorous shaking gave a dark blue solution. Of course, that means that we started from R here, so R was the complex with 2 hydroxides and 4 water. We added ammonia to it, and we also got the dark blue solution. When we add ammonia to that complex, then T must be the complex between copper and 4 ammonia and 2 water, or just 4 ammonia. And that means we started with the copper plus 1 complex from the copper 1 iodide. On shaking, it was oxidized to copper 2 plus. Then we said S was copper oxide. When we add nitric acid to it, what would be the blue solution? Of course, the blue solution is the copper 2 plus in solution, which is the copper with 6 water complexes. Copper 2 plus with 6 water complexes. So overall, when we're told to identify, we found that P is the copper metal, Q is the complex with 6 water, R is the complex with 4 water and 2 hydroxides, S is the black solid, the copper oxide, T is the complex between copper and ammonia and water, copper 2 plus, T is a copper 2 plus complex, and V is a copper 1 complex with ammonia, and of course W is the copper with 6 water ligands, copper 2 plus. T and V are the same type of chemical species. This was T and this was V. What type of chemical species do we talk about here? These are called transition metal complexes. Explain why T is colored, V is colorless. Now, we said, and we want a detailed explanation of the fact that T is colored is not required. So, for our explanation, we know that originally the 5d orbitals should be of equal energy. But when the central metal ion makes complexes with the ligands, the 2 of the d orbitals split and have higher energy than the rest of the d orbitals. When this d sublevel is not filled, if it is incomplete, then electrons from the lower d orbitals will absorb energy, jump to the higher d orbitals, and the rest of the visible spectrum is transmitted, and that is what we see as a color. So if we're talking here about copper, we know that copper atoms have for S1 3d10. We said before it was supposed to be for S2 3d9, but then we take 1 electron from the 4s to make the 3d complete. So this is the electron configuration for copper atoms. Now when we form copper plus 1, we remove the electron that was in the 4s. So we still have a filled 3d sub-level, and that means this is not going to be colored. Now copper 2 plus, we take another electron, so now the 3d is 3d9. Now they're incomplete. Now they will absorb from the visible spectrum, and the copper 2 plus complexes are colored. So the difference between T and V is that in T we have copper 2 plus. The 3d orbitals are incomplete. When light shines on the solution, an electron absorbs an amount of energy and jumps to the d orbital at the higher energy level. The rest of the visible spectrum is transmitted, so we see a color. While in copper plus 1, the 3d orbitals are full, no electron transition to higher d orbitals, so no color is observed. So just an explanation for the change of V into T on shaking. Which one was V and T? We were talking about this part of the flow chart, and we said V is the copper plus 1, and we said it's colorless, and when it is shaken vigorously it becomes dark blue solution, and we said that is the complex we're talking about. How did V change into T? we should realize that copper plus 1 is oxidized by oxygen in the air when it is shaken to form copper 2 plus. Then the reaction between copper 1 iodide and sulfuric acid is a disproportionation reaction. So we said copper plus 1 with sulfuric acid forms, we said P was copper and Q was copper 2 plus. Write the ionic equation for this disproportionation reaction. So what do? We start with copper plus 1. It changes into copper metal, so that is from plus 1 to 0, so that is reduction. And Q, which is copper 2 plus, so that is oxidation, and you need to balance the equation. Show that the reaction is thermodynamically stable. Use the standard electrode potentials of the cells from the data booklet. So if we look at the data booklet, we have copper 2 plus electron to give copper plus 1, that is plus 0.15. We need to invert that because our reaction is from copper plus 1 to plus 2. So that means the E of that cell is minus 0.15. Now the other change was copper plus to copper metal, that from the data booklet is plus 0.52. The overall E cell for this reaction is plus 0.37. That is a positive value, and so the reaction is feasible. The rare mineral, this has chemical formula that 4.26 grams of the mineral was dissolved in distilled water and the solution made up to 250 centimeter cube. Excess potassium iodide solution was added to a 25 centimeter cube portion of the solution, and the iodine formed was titrated against a solution of sodium thiosulfate with this concentration. This procedure was repeated until concordant results were obtained, and the mean titer was 26.65 centimeter cube. We're given the equations and we're told to calculate N, which is the number of moles of water of crystallization per mole of that compound. So, what's the first thing we should do? We should get the number of moles of thiosulfate. We have the concentration, we're given the concentration of the thiosulfate is 0.05. We're given the titer, 26.65, so divide by 1000 to get it in decimeter cubed. This gives us the number of moles of thiosulfate. Then we look at the equations. The second equation below there says that number of moles of iodine should be half of the thiosulfate. 2 thiosulfate reacts with 1 of iodine. So the number of moles of iodine should be half of this. But then that first equation says then the number of moles of the copper 2 plus should be twice of the iodine. So overall, the number of moles of the copper 2 plus is actually the same as the thiosulfate. Now this is in the 25 centimeter cube portion. So we need to get it in 250. So you multiply by 10, that would be the number of moles in 250, so that is in all the solution. Now we know that all of this solution had 4.26 grams, so I can get the MR. I know the number of moles, I know the mass, so I can get the MR, mass over number of moles. That gives me a total MR of 319.7. I can use that to get the N. I know we have 2 potassiums, 1 copper, 4 chlorines, plus the part of the water, which we're going to call 18N. That is the MR of H2O times N. So the total of that is 319.7, and solve for N. So if we solve for N, N comes out to be 2. So that is the number of moles of water of crystallization. Question 20 says, ketones are useful starting compounds in organic synthesis. The mass spectrum of butanone that were shown has significant peaks at m over z43 and m over z57. So this is mass spectrum. Give the structures of the species responsible for these peaks. So we try to decide which fragments would give m over z43. We find that that is the fragment, and remember, when we write fragments in the mass spec, they are positive ions. The other one, we want something that's 57, so that part is 57. Okay, give the structure of one other species that you would expect to produce a peak at a different m over z in the mass spectrum of this compound. So, we already got the parts we talked about. Let's talk about something else. For example, the part that has the CH3 alone with a positive charge, the part that has the CH2, CH3 alone, or this part, all of it. So any one of these, you should get a peak for these fragments. Devise a reaction scheme to prepare propane 1-ol from butanone using no more than 4 steps. So we're trying to start with butanone and we want to get propane 1-ol. This is how we answer the question. Write what is required first, and then we try to go from the reactant to the product. Identify reagents, essential conditions, and give names of the structures of each of the intermediate compounds. So, we're starting with butanone. Obviously, we need to remove one of the carbons. So that's the main job that we need to do. So, starting with butanone, to remove one carbon, I can react it with alkaline solution of iodine, because I have the part that is CH3 C double bond O. The methyl ketone part, react with iodine in sodium hydroxide. It will cut off that extra carbon and will give the sodium salt of the rest. So that is sodium propanoate. We're required to give the names. Then what should I do next? I can add dilute acid. So this becomes propanoic acid. Now, we're trying to make what? We're trying to make propane 1-ol. I can reduce this lithium aluminum hydride in dry ether. That would change the acid into alcohol. The other question says, devise a reaction scheme to prepare 2-methyl-butene. So we're trying to prepare 2-methyl-butene from butanone using no more than 4 steps. Again, we want to start with butanone, but here we're trying to add an extra carbon. The final product here has an extra carbon. That means we need to use Grignard. So we're trying to add one extra methyl group. So we start with methyl bromide with magnesium in dry ether. That gives me the Grignard reagent. This reacts with the butanone. It adds that extra methyl group. Now we're trying to make what? We're trying to make an alkene from this. So dehydration, concentrated acid, and heat. The acid could be phosphoric acid or sulfuric acid. Heat, this would give the required product. A yellow crystalline solid dissolved in distilled water to give a yellow solution. So E is yellow and it gave a yellow solution. Addition of dilute sulfuric acid produced orange solution. Warming of that orange solution with ethanol resulted in a green solution and formation of ethanol. A standard cell was set up using solutions of F and G for the right-hand electrode and ethanol and ethanol for the left-hand electrode. The E cell for that was found to be plus 1.97. We are given the equation for ethanol going to ethanol. Deduce the formula of the ions responsible for the colors F and G using standard electrode potential and the E node given and the values in the data booklet. We should know, first of all, that if I have a yellow solution and I add acid and becomes orange, we're probably starting with chromate. If we add acid to chromate ions, which are yellow. It becomes dichromate, which is orange, and then this, when they warmed it and so on, this became green. The green solution would be the chromium 3+. Now, we look at the data booklet, we find that there is an equation for dichromate going to chromium 3+ with this E cell. Using the other equation we're given, ethanol to ethanol, the overall E cell is plus 1.94, and that was what was given up there, so this is correct. Write the overall equation for the reaction. Well, we have dichromate going to chromium 3+, and we have the ethanol going to ethanol. Remember, we need equal number of electrons in order to add them up. So that second equation, we're going to multiply by 3 all through so that the number of electrons is the same. And then we cancel the number of electrons. We cancel some of the H plus because we have H plus on both sides of the arrow. And this would be our overall reaction, or overall equation for the reaction. Write the ionic equation for the reaction of the solution of E with dilute sulfuric acid. E with dilute sulfuric acid was the chromate going to dichromate. So we're starting with chromate going to dichromate. We want to write an ionic equation for that. Well, you should balance. We need water on one side and H plus on the other. Remember, we're doing this in dilute sulfuric acid, so the H plus has to be before the arrow. And then we check to make sure it is balanced. It's not balanced. We need to put a 2 in front of the chromate. Now, is it balanced? Yes. Using excess oxygen, 25 centimeter cubed of a gaseous hydrocarbon, so we don't know what is X and what is Y, was burned completely. After cooling to room temperature, the total gas volume was measured and found to be 75 centimeter cubed less than the total gas volume before the mixture was ignited. When the product gases were shaken with potassium hydroxide solution, the total gas volume decreased by 100 centimeter cubed. All gas volumes were measured at room temperature and pressure. This is the general equation, and the question is, determine the formula of CXHY. So this was the equation, and we're required to get what is X and what is Y. Well, what did the question say? The first hint here is, when the product gases were shaken with potassium hydroxide, the total gas volume decreased by 100 centimeter cubed. Remember, when we shake this mixture, potassium hydroxide, it reacts with which one? It reacts with the carbon dioxide gas, which is acidic. So if the volume decreased by 100, that means that the volume of the carbon dioxide was 100. We were told that we start with 25 centimeter cubed of the hydrocarbon. So 25 centimeter cubed gives 100 centimeter cubed. Again, this is at room temperature and pressure, and these are gases. So we can relate the volumes directly. That means 1 mole of the hydrocarbon would react with 4 moles of the carbon dioxide. So that means X is 4. So that's it. Now, what is Y? We are also told that after cooling to room temperature, the total gas volume was found to be 75 centimeter cubed less than the total gas volume before the mixture was ignited. So that means we started with 25 centimeter cubed of the hydrocarbon. That will react with what? It will react with 25 times the coefficient of oxygen, plus there was excess oxygen. Now, after the reaction at the end, the volume was found to be 75 centimeter cubed less than the total gas volume. So at the end, what do we have? we have the excess oxygen, which we did not use, plus the 100, which was the carbon dioxide, plus the 75 centimeter cubed, which was the difference between them, and we solve for y. We know already that x is 4, so we have x is 4. Now we're trying to solve for y. Of course, excess oxygen remains before and after the reaction, so it doesn't make a difference with the volume, and we get that y from all of this calculation, y is equal to 8, and that means the formula of the hydrocarbon was C4H8. When CXHY was added to a little bromine water, the mixture shaken, the bromine water remained yellow. So we are told now that the formula is C4H8, but it is not an alkene, because if it were an alkene, it would change the bromine water to colorless. So it's not an alkene, doesn't have a double bond, but it is C4H8. So what is the possible structure of this compound? Well, you should realize C4H8 is the general formula CnH2n. This applies to alkenes and to what? Cyclic alkane. Remember, the cyclic alkane has the same general formula as alkenes. So cyclic alkane with 4 carbons could be either this cyclobutane or something like this, in which we have cyclopropane with a methyl group on one of the carbons. So these are the 2 possible structures for the C4H8. Compare and contrast the mechanism of action of platinum as a catalyst in the removal of pollutants from car engine exhaust fumes with that of vanadium oxide as a catalyst in the contact process for manufacture of sulfuric acid. Remember, we said we use platinum in the car engines and we use vanadium oxide in the contact process. We're told to compare and contrast. Remember, both of them are heterogeneous catalysts. The platinum with the car engine gases, and the vanadium oxide is a solid with gases that are used in the contact process. So both of them are heterogeneous catalysts, and you should realize that in the catalytic converter, what is happening? The reactants of carbon monoxide and oxides of nitrogen are adsorbed on the surface of the catalyst. This weakens the bonds and the reaction occurs easily, and then the products, carbon dioxide and nitrogen, are desorbed from the surface of the catalyst. So this is how the catalytic converter changes the harmful gases, which are carbon monoxide and oxides of nitrogen, into safer gases, which are carbon dioxide and nitrogen. Now, the contact process. What was the contact process? It was the reaction of sulfur dioxide with oxygen to give sulfur trioxide. And we said the catalyst in this case is V2O5. So what happens is the V2O5 first reacts with the sulfur dioxide. It is reduced, and the vanadium species that is formed is then oxidized by oxygen, and the V2O5 is regenerated. Coffee chemistry. There are over 1,000 chemical compounds in coffee, and their physiological effects are the subject of considerable speculation and research. The verdict on coffee is contradictory. Some of the compounds have been identified as toxic and even carcinogenic, but others are antioxidants associated with cancer prevention. Recent research has identified compounds in coffee that might be used in the treatment of prostate cancer. By far the best known compound in coffee is caffeine, the most widely consumed psychoactive drug in the world. In small amounts, it is a stimulant, but doses in excess are toxic. caffeine contains amide and amine groups. Now, what are we required to do? We are told that chlorogenic acid is responsible for the acidic taste of coffee. It is an antioxidant and has also been shown to slightly decrease blood pressure. Caffeic acid, quinic acid, and acetone are all present in coffee. Another way of drawing the structure of caffeine is shown. Now, they drew it at first like this, but then we're told that we can also draw it like that. The bonding represented by this diagram of caffeine differs from that given in the passage. Explain what this diagram indicates about the bonding in caffeine, stating the effect on the structure of caffeine. So instead of drawing caffeine with individual double bonds, we can draw them with the double bonds delocalized around the 5-carbon parts, the 5-carbon section of that molecule. So in the 5-sided ring, the electron pair on the nitrogen is delocalized with the pi electrons of the double bond, making the structure stable so that all the CN bonds are the same length. Suggests why caffeine is a much weaker base than a primary amine such as ethylamine, even though right-hand ring has 2 amine groups. Now, of course, we said to be a base, the lone pair of electrons on the nitrogen should be available for dative bonding with an H+ ion. But we just said that these lone pair of electrons on the nitrogen have been delocalized. So the lone pair of electrons on the nitrogen are delocalized in the ring, so they are less available to form a dative bond with the H+ ions. A 200 centimeter cubed cup of coffee contains approximately 85 milligrams of caffeine. Calculate the concentration of caffeine in this cup of coffee. Give your answer to an appropriate number of significant figures. Okay, to get concentration, what should we do first? We have 85 milligrams and we have 200 centimeter cube. The first thing we need to do is get the MR of caffeine because we're going to use that. So the MR of caffeine comes out to be 194. Please make sure that you can do this. Translate that structure into formula that you can get its MR. And then we need to get the number of moles. We have 85 milligrams, so that's 85 times 10 to the minus 3 of a gram, over the MR that we got. This gives a certain number of moles of caffeine. We want concentration. Concentration is number of moles over the volume. Of course, the volume has to be in decimeter cubed. So we divide the 200 by 1000 and we got this concentration in mole per decimeter cubed. The removal of caffeine from the body is a first order reaction with a half-life of between 3 and 7 hours for an adult. An adult drinks coffee containing a total of 160 milligrams of caffeine. Calculate to the nearest hour the minimum time needed for the amount of caffeine in their body to drop to 20 milligrams. So we are told it is a first order with a half-life of between 3 and 7 hours. We want the minimum time needed, so we're going to take the 3 hours part. So the first half-life, 160 over 2 half-life means we're going to divide it by 2. So the first half-life will give 80, the second half-life will give 40, the third half-life would be 20 milligrams. So I need 3 half-lives to get to 20. Now, these 3 half-lives will take how long? If we take the 3 hours, if we're going to say that the half-life, each half-life is 3 hours, then that means it will take 9 hours to drop to 20 milligrams. Chlorogenic acid is an ester of caffeic acid, a compound that is present in all plants. A student suggested that caffeic acid could be synthesized by electrophilic substitution of 1,2-dihydroxybenzene. So we want to start from 1,2-dihydroxybenzene to form that caffeic acid. Draw the mechanism of this electrophilic substitution, including the formation of a suitable electrophile. Of course, if I want to change this to the caffeic acid, that means I need to add that part to the 1,2-dihydroxybenzene. How do I add it to a benzene ring? We start with the chloro compound of that in presence of aluminium chloride, which is the catalyst. This forms the electrophile, and this electrophile can then be attacked by the benzene ring, and then we remove the electrons, we remove the hydrogen using the electrons to change the benzene ring back to its original state. So this is the mechanism of any electrophilic addition reaction with benzene. Deduce the structure of quinic acid, which combines with caffeic acid to form chlorogenic. So we're given the structure of caffeic and we're given the structure of chlorogenic. Now, what do we want to react with the caffeic acid to get that product? We need that part, and that part would be in the form of an alcohol so that it reacts with the acid part of the caffeic acid to give that product. The structure of acetoin is shown with one of the proton environments labeled. So one of the protons on the methyl group is labeled A. Identify the other proton environments of this compound and label them B, C, D, and so on. So let's look at this compound. The methyl group next to the carbonyl is one type of proton environment. We also have another methyl group on the right, so we label that C, or you could label it anything. B is, I labeled it the carbon that is next to the carbonyl on the other side, and the D is the hydroxyl group. And then the question says, complete the table to show the splitting pattern in the high resolution proton NMR of this compound. So A, what would be the splitting pattern of A? There is no proton on a neighboring carbon, so A, the protons of A would be singlets. Now, B, what is B? B has a methyl group on top, which we labeled C. So that is 3 hydrogens on the neighboring carbon, so that should be a quartet. The C has the proton of B next to it. That is 1 proton, so the C would be doublets. The hydroxyl, the hydrogen of the hydroxyl group is always a singlet. And that's the end of this paper. I hope this was useful to you and you understood all the parts. Thank you for listening and good luck on all your exams.